So folks, I want to continue on with looking at Newton's second law, and we're going to now elaborate on our model in such a way that it can take into account some sort of resistance force that varies proportionally with some power of the velocity. So we could be thinking of something like air resistance here. So let's go ahead and make sure we understand the issue. Let's suppose that our object is falling. Okay, so here's the Earth or whatever larger body that this smaller body is tending towards. And so the object is falling in this case, and that matters. And so if we do a force diagram here we have the force due to gravity on this, which is always towards that larger body. And then in this case, in fact, so let me just say that's equal to our minus mg. And notice that this force is always negative. Regardless of whether the object is moving upwards or downwards or some sort of trajectory, the force due to gravity is always towards that larger body, in this case the surface of the Earth or whatever you want to consider it. But the resistance force is always opposite the direction of motion. So here we've got a resistance force, and this is always opposite the direction of motion. And the fact that this is always opposite the direction of motion means that you really cannot be on autopilot as you're working through these problems when you're taking into account air resistance, because you need to be adjusting the coefficient in front of the force so that it's always computing a value that is opposite. So for example, if this is falling, it has a negative velocity, then you want to ensure that this force resistance is positive. Likewise, if the object were moving upwards, let's just do that. If the object were moving upwards like this, here's the object, then the force due to gravity would still be downwards just as it always is, but so would our resistance force because it's opposite the direction of motion. And that's where you've got to be a little bit careful with this, and I'll address that in a moment. So in working with Newton's second law, we eventually arrived at something like this in the last video, that m dv dt was equal to the sum of the forces. And in the first example we looked at, the only force acting on it was the force due to gravity. But now, of course, we've got two forces. So we've got the force due to gravity plus the force resistance, or the resistance force, the air resistance force, or whatever you want to consider that. And let's go ahead and fill in a few details. So we've got the mass times acceleration. Remember, dv dt is acceleration there. And this is negative mg. That's the force due to gravity. And if we're considering upwards positive and g, if g is the number 9.8, that's what you're using, or 9.81 or 32, then you need this negative sign, right? So we need this negative sign here. And then what I'm going to do, and here's where I'm going to deviate from the author, I'm always going to put a plus sign here. The author will sometimes put a plus sign there and sometimes put a minus sign there, and I'll talk about that. But I'm always going to put a plus sign there, and then we have k times v to the p. So the way we think about our resistance force is it's always some constant of proportionality times a power of v. And what is that power of v? Well, that p-value could be anything between 1 and 2. When Newton imposed certain conditions, he was able to, and made certain assumptions, he was able to derive that the air resistance force was proportional to the square of the object's velocity. But in fact, if you don't make certain assumptions, and if you verify things experimentally, you might find that there's some p-value between 1 and 2 that works better than using 2 itself. So depending on your problem, you may use 1, you may use 2, you may use any real number in between there, depending on your model. And we're not going to get into that too much, but you'll have to watch out for that in the problem statements. Okay, so our author says k is always greater than 0, and then changes the sign in front of k. And that's a perfectly fine thing to do, and I see his rationale for it, but I find that a little bit hard to keep track of. So I would rather always put a plus sign there, and then I'm not going to impose the condition that k is positive. Instead, I will adjust the sign on k in order to ensure that the force resistance, like we said here, is always opposite the direction of motion. And so that's where you've got to be a little bit careful here, folks. So, for example, Notice that if I pick p equal to 2, then v squared is always positive, and I would just simply assign k to be opposite the direction of motion. So if this is moving upwards, then I want k to be negative. So it's a negative force resistance. And if this is moving downwards, then v squared is still positive. And so I would need this to be also is a positive force, because if it's going downwards, we want this to be a positive upward force. If p is 1, though, you would then change the sign on k appropriately. So that's what I'm saying here. There's a little bit of an issue in choosing the sign on k, and we're going to have to deal with that. So watch out for that. All right, the very last thing to say about these problems is that our author doesn't like to leave the differential equation this way. Instead, the author likes to divide over the mass. Fine. And we get minus g plus, and then the author's going to put a rho, that's a rho here, rho v to the p. Where rho, first of all, that's, if you haven't seen that, that's the Greek letter rho, so it's spelled R-H-O. And in this case, rho is equal to k divided by m, whatever k is divided by m. So you can see here I've used that Greek letter rho. It looks like a P, but it's actually a Greek R, is the way we interpret that. And so it's pronounced rho, and it's made by sort of making an R, but then twisting the top of the R kind of in on itself like that. Okay, so now I think we're ready to return to our examples. So I've slightly modified the example in the textbook, and here we have our same crossbow from before. It's still being fired upwards with the same initial velocity from the same ground level, so that part hasn't changed, same initial velocity. But now we're going to suppose the air resistance varies proportionally with the velocity. Careful there, I'm not saying the velocity squared or some other power. And that the rho component is experimentally determined to be negative 0.04. So what are we saying? We're saying that this is our differential equation right here. dv dt is equal to negative g and then minus 0.04 v, where I'm using v to the first power because it varies proportionally with the velocity and not some other power. Now I just want to check something here. I picked my rho to be negative. Let's see if that was an appropriate decision. Well, if this ball is heading upwards, then here would be our free body diagram. We'd have the force due to gravity pulling down on it, as it always does, as well as the air resistance force needs to be negative. Well, let's just check that. If this is moving upwards, the velocity is greater than 0, so that's a positive component, times this negative number gives me that negative force resistance that I wanted. That's good, that works. Now let's just check to make sure it works if we're going in the other way. If this object is moving downwards, then the velocity is negative. So if we draw our free body diagram here, we still have the force due to gravity pointing downwards, and we would expect the resistance force to be a positive force because it's acting opposite the direction of that negative velocity. Well, if this object's falling, the velocity component's negative, and the k value I chose to be negative, or actually this is the rho value, the k divided by m, is negative, and the product of two negatives is a positive. So when this object is falling, this component, although it may not look so, is actually positive because that velocity value would be negative. So everything works out there. Be a little bit careful with that. I found that a little bit tricky. Okay, so finally we're ready to solve this differential equation. So let's see here. We've got that dv dt is equal to, and here maybe I could have put this in sooner, but let me just put it in now, negative 9.8 minus 0.04 v. And in this case, we have a separable differential equation. We would have that dv over negative 0.04 v minus 9.8 is equal to differential t. Integrating both sides, I get 1 over negative 0.04 natural log absolute value of negative 0.04 v minus 9.8 is equal to, we are integrating the right-hand side as well, so we get t plus c. Okay. All right, my screen's frozen here, folks. All right, there we go. And let's see here. So first of all, let's take care of this 1 divided by negative 0.04. So that's 1 over 4/100ths, which is the same thing as 100 over 4. So this is negative 25 natural log absolute value of negative 0.04 v minus 9.8 equals t plus c. And if we divide over that negative 25 and, well, let's just do the steps, each step one at a time. Feel free to skip forward if you want to. So I get negative t over 25 plus, because I don't have any other constants there, dividing c by 25, I just call that it's just a new constant. And exponentiating and using some tricks we've done a couple of times, I end up with the negative 0.04 v minus 9.8 is equal to ce to the negative t over 25. And finishing out to solve for v, I get v is equal to 9.8 divided by negative 0.04 plus ce to the negative t over 25. Or that v is equal to negative 245 plus ce to the negative t over 25. And then let's see here. We know that when t equals 0, so we've got the order pair 0, 49, that is v of 0 equals 49. So we would have that 49 needs to be equal to negative 245 plus c e to the 0 is just 1, or that c needs to be equal to 294. So let's see here. That gives us that v of t is equal to negative 245 plus 294 e to the negative t over 25. And then to continue solving for, well, that's our velocity function. We're all set there. That's good and ready to go. We found the velocity function. But if we want to find the position function, we need to recognize that this itself is a differential equation. This is ds dt, or actually our book would use dy dt. And so integrating both sides again, we get y of t is equal to negative 245t plus 294, and we're integrating here, so we'd have to divide that by a negative 1 over 25, so that's the same thing as multiplying by 25. And if we do that, that's actually 7350. So plus 7350 e to the negative t over 25 plus another constant. Now, what's our other initial condition? Our other initial condition is y of 0 equals 0. Here, of course, we got to be a little more careful when we plug in 0 into this equation. So let's see, if I plug in 0, the first term zeroes out. The second term would just be the constant 7350 plus c. And so then we get that c needs to be equal to, oops, I'm sorry, folks. When I divide by negative 25, that should be a negative sign here. So we get this is a negative sign, and so then we would find that c is equal to 7350, and long last we can give our position function y of t is equal to 7350 minus 245t minus 7,350 e to the negative t over 25. And there at long last is our position function. Okay, this has been a long video, folks, but I actually have one more thing that I want to talk about, and because now's a really good time to talk about it since we've just done this. Here was our, from before, here was our velocity equation. And notice that it has these two components. It's got a constant term, and then it's got this exponential term, and that exponential term has a negative power to it. So find some room if you can. Let's look at the limit as t goes to infinity of v of t. That is, let's consider this object falling for a long time. Now, in reality, because this was a bolt shot upwards, it would eventually come back to the surface of the Earth, so this wouldn't quite work. But let's suppose we shot it, here we are, and we shoot the bolt upward, and we've got a cliff that it can keep falling much, much further downwards. So let's look at the limit as t goes to infinity for this velocity function. Well, if we do so, notice that the limit of the constant is just the constant, negative 245. And what happens to this term right here as t gets large? Well, e to the minus a large number is a very, very small number. And so this term eventually goes to 0. And so I hope you see that this term right here would go to 0 as t gets large, and so we just get the constant negative 245, and this is what is referred to as terminal velocity. So if this object with wind resistance continued falling, let's say we were very high up on a mountaintop with a cliff facing downwards, and it could fall as long as it wanted, eventually it would stop accelerating. And why is that? That would be because the resistance force would be equal to the force due to gravity, and you would no longer have any acceleration in the system. And when that happens, you would be at a velocity of negative 245 miles per hour. So if you were to chart this object's speed, it starts out with that positive speed of 49 meters per second. So here's 49, and it would then be decreasing exponentially, but there would be an asymptote here at the value negative 245, and it would approach that asymptotically as t went to infinity. And there is the representation of terminal velocity, which maybe some of you have heard of in your physics classes. So anyway, I hope this was a good demonstration. Let me know if you have any questions.